Okay, let's work through some of these problems. Okay. So there's a mix on here. There's a couple of calculations that you really have to do. And then there are some that you're supposed to know, but they're not really calculations. So, and I've kind of doubled up where I can so that we can do some on the board, but then there's still space for you to work through some of these on your own. Oh, and so at the top, chapter 15 and 16 are questions that I picked out from the textbook. You should at least look at them. Some of these are going to be describe what an acid is versus perform some kind of calculation. Do as many as you can. Now, it's got to be like half of them are actually on this sheet anyway, and then half of those we're going to do. But you'll notice for chapter 15, but not for 16 because I learned my lesson, for chapter 15 each question has two sets of numbers. The number on top is the number in the 10th edition, that's the book that we're using, and then the number below is cut and paste out of the 13th edition. By the time you get to chapter 16, I learned not to cut and paste the question numbers. But I was using the old numbers to keep track of where I was, and when I realized I actually wasn't doing a very good job of that, I stopped bothering. So, chapter 15, questions 13 and 14 both ask the same thing. So I'll do some of these, and then it will be up to you to complete the rest, and then turn this in. Find the K expression. So, K is always concentration of the products divided by the concentration of the reactants. So, if, as is in 1513, part A, your reaction says 3 nitrogen oxides are in equilibrium with a nitrous oxide, N2O, plus a nitrogen dioxide. That's an oh, are we missing? No, 2 nitrogens here. Okay. K equals, these are my products. That's my reactant. And then you raise it to the power of its stoichiometric coefficients. There are 3 nitrogen monoxides in the balanced equation, therefore it gets raised to the power of 3. Methane, gas, plus 2 molecules of hydrogen sulfide, gas. Make 1 molecule of carbon disulfide, gas, plus 4 molecules of hydrogen, gas. Okay, is products divided by reactants, all raised to the power of the stoichiometric coefficients. So on the product side, I have the concentration of CS2, carbon disulfide. And then I have the concentration of H2, raised to the power of 4. And then over on the reactant side, which goes underneath, I've got the concentration of methane, divided by the concentration of hydrogen sulfide, and I have 2 of those, my balanced equation. Therefore, that's going to be raised to the power of 2. Last one. Nickel. Tetracarbonyl as a gas is in equilibrium with nickel as a solid and 4 molecules of carbon monoxide gas. Okay. Products divided by reactants. So here's my products. Concentration of nickel times the concentration of carbon monoxide raised to the power of 4 divided by the concentration of nickel tetracarbonyl. Take out your red pen. Doesn't have to be red. That's a solid. It has no place in the equilibrium expression because solids don't have concentrations. Okay. So that leaves you question 1514 to complete for me. There is no trick. Same thing. Question 1515 says, when the following reactions come to equilibrium, does the equilibrium mixture contain mostly reactants or mostly products? And there's a first reaction, reaction A, and then there's a second reaction, reaction B. And reaction A has an equilibrium constant of 1.5 times 10 to the negative 10. That's less than 1.00. Therefore, the equilibrium lives on the left. Reactants don't turn into products very much. The second equation has a value of 2.5 times 10 to the 9. That's a big number. Therefore, in that equilibrium, there are significantly many more product molecules than there are reactant molecules.
Can I ask you a question on that one really quick?
Do it upside down.
No, at the end of the question, it's just asking to indicate whether it's homogeneous or heterogeneous.
Oh, okay.
And if it's, they're, like the first two are homogeneous, right?
Yeah.
Because they're all gas.
Mm-hmm.
And then that last one is heterogeneous.
I didn't read that. There you go. In each case, indicate whether the reaction is homogeneous or heterogeneous. So there's my K prime, and then here's my K. That one's heterogeneous. Hetero meaning different, homo meaning the same. Okay, that leads us to 1517 and 1518, which are the long-awaited turn Kp into Kc or turn Kc into Kp. Mentioned it in class, said it wasn't going to be a very big deal. Here's a couple of examples. Plus, this is also a subpart of 1522, which is misnumbered on your sheet as 1529, also known as 1526. We'll get to it when we get to it. Okay, so I'll do one of these, both the same. One finds Kc and the other one finds Kp. Let's do 1517 and leave you 1518 to do. Okay, so 1517. says Kc. Actually, you're much more likely to encounter it coming the other way. You're much more likely to find, here's a value of equilibrium constant that was found using pressures. Make this number slot into the big table of equilibrium constants that you've got that were found by concentration. But you'll see as we progress, it's no big deal. So Kc is 0.042, no units. My reaction is PCl3, which is a gas, plus chlorine molecule, which is a gas, makes PCl5. So I turn phosphorus trichloride into phosphorus pentachloride. And because I've quoted an equilibrium constant, I need to quote a temperature. Let's convert that Kc into a Kp. Now, the equation for that is that Kp equals Kc times RT, all raised, that RT term is raised to the power delta N. Let's go figure out what that is. Delta N is the number of moles of product minus the number of moles of reactant. Number of moles of product is 1. Number of moles of reactant is 2. I have 2 reactants and 1 product. So that is 1 minus 2, which equals minus 1. Fortunately for us, this question gave us temperature in Kelvin. It gives it to you in Celsius. You have to add 273. And then R, what is R? R is the universal gas constant. What's the value of R? Yeah, we just used it last week and it was 8.314 joules per mole per Kelvin. But that was last chapter. At the end of General Chemistry 1, when we did gas reactions, we also used R because it was in PV equals, oh, remember, I actually started writing it out on the board. I did. I derived where we get this reaction, this equation from. And it came from PV equals nRT. And the R in PV equals nRT is not the 8.314 joules per mole per Kelvin. That's the, anybody remember what that one is? Is 0.0821 moles per liter. Moles per liter atmosphere. If we want to know what the units for R is, okay, those moles is R, so it's going to be P. So, oh, there's a Kelvin missing also. So that is liter atmospheres per mole per Kelvin. Easy. There it is. liter atmospheres per mole per Kelvin. Okay. You don't have to remember everything. You can always figure it out. So that's 0.0821 liter atmospheres per mole per Kelvin. And then one of these numbers we know and the other one we don't. Slot the numbers in. Let's go. Which one do I know? I don't know Kp, but I do know Kc. So Kp is Kc, which is 0.042 times RT. R is 0.0821 liter atmospheres per mole per Kelvin times 500, all raised to the power of -1. Now you can do this in your calculator, or you can do this now. Think of a number, any number, make it a simple number. In your head, raise that number to the power of -1. And what have you got?
The inverse.
Yeah, 1 over that number. So if the number I was thinking of was 2, and I raised it to the power of 1, what I get is 1 over 2. So I could do this in my calculator and raise this to the power of -1, or I could just scoot it down. There you go. That's my answer, whatever that answer is. So 0.042 divided by 500 times 0.821. Most of those numbers are going to cancel to give me almost unity. It should be about 0.001. We only have 2 decimals, 2 significant figures. So the Kc was 0.04, and the Kp is 0.001. So those numbers are different. Okay? They do differ from one another, and you can't just throw a Kp into a table that is full of Kc's. You have to do something to convert it. All right, that leaves you, was it 15, 18 to do yourself? Okay, on the next page there is a question, and then there's another question underneath it that looks very, very much like it. The reactions are different, but the questions are the same. The questions say, what is the value of Kp for this reaction? Top one says Kc, bottom one says Kp, don't matter. And then what is the Kp for this reaction? And you find out that the second reaction is the first reaction written backwards. And then the next question is, what is the value of this reaction? And the reaction is half of the number that you started with. So let's do that. So this is 1522. The previous one, what was that? Did I say that was? 1517. That one right there was 1517. It's 1522. Which on yours is called 1529, and then underneath it says 1526. It's actually 1522 from the book. shows you a reaction, and it says 2 chlorine gas molecules plus 2 steam molecules. They're waters, but they're in the gas phase. Makes 4 hydrogen chlorides. They're not hydrochloric acids because they're not in solution. They're in the gas phase. That makes them covalent molecules. They're hydrogen chlorides. Plus 1 oxygen gas. It tells me somewhere that this reaction is occurring at 480 degrees Celsius, and that the value of Kp for this equilibrium is 0.0752. Okay. And then, so I've got a Kp in the question. It asks, what's the Kp for the reverse reaction? That's the reverse. Some data is given to you in the question for a reaction moving from left to right. Then they take that question and turn it around and ask you to find the Kp. Well, K reverse is 1 over K forward. So the Kp here is 1 over 0.0752. Gives you the value of Kp in the question. Let's just look at it. 1 over. That's 13.3. Okay, the next part, it asks you to do something that I really, really don't like. Sometimes you cannot avoid it because it's the way that data tables in textbooks are written, but I'm not a fan of writing reactions this way because they don't exist. What it's done is it's said, what would, which way am I around now? We're back to it being the first way around. So, here I have a 2, and I have a 2, and I have a 4, and I have a 1. If I wanted to know, and it will come up from time to time, instead of knowing just a value, I will try to want to make it a value per reactant. I want to turn that 2 into a 1. So, can we go ahead and divide all of our numbers in the question by half? I am not a fan of this because there is no such thing as half a molecule of oxygen. There's no such thing. You can't have half a molecule of oxygen. But there are times when reactions are written out in the half molecule form. So it says, given Kp equals this for twice the reaction, what would Kp be for half of that reaction? you just take your Kp and you raise it to the power of a half. If you were doubling all of these numbers, you would raise it to the power of 2. If you came through and you tripled all of these numbers, you'd raise it to the power of 3. So under this case, you take the Kp and you raise it to the power of a half. Do you know what happens if you raise to the power of a half? It's the inverse. So if you took a number, here's a number, and you raise it to the power of 2, obviously you get the square. What if you did the opposite of raising it to the square? The inverse of raising it to the square. Raising a number to the power of a half is the square root. So you just take the root of that number. And I'm not a fan, I'll write it down so that you can keep track that it is what you think it is, but I really don't like this. So that would be 0.0752 to the half, which turns out to be 0.24, 0.274. And then in part 3, it says, now what's the value of Kc? You've just found Kp in part B. Go ahead and find out what the value of Kc would be for that. We just did that on the board. But what you would do is you would count now your delta n is 2.5. It used to be 5, and it used to be 4. But now it's 2.5, subtract 2. So your delta n in the red numbers is only a half. Okay. Oh, why didn't I write that out? Okay, 1527. 1527, lots of words, but all you have to do is write out the formula and put the numbers in the right box, because all of the numbers are present. Okay, let's do that. We did one of these in class earlier on. This is the last time they're going to be this simple. We're going to start to get, what happens next is, after we give you all the numbers and say find the missing number, we're going to only give you, we're going to infer what's going on by giving you partial information, and then you're going to solve a problem by logic, and then you're going to find the missing numbers. It's more fun. So this is 1527. 1527 says gaseous hydrogen iodide is placed in a closed container at 425 degrees Celsius, where it partially decomposes to hydrogen and iodine. Then it gives a formula, gives an equation. It says 2HI as a gas are in equilibrium with H2, that's gas, and I2, that's gas. And at equilibrium, we have found that the concentration of HI is 3.53 times 10 to the negative 3 moles per liter. That the concentration of H2 is 4.79 times 10 to the negative 4 moles per liter. And that the concentration of iodine is is 4.79 times 10 to the negative 4 moles per liter. Find the value of Kc. Okay, now before we proceed, isn't it a coincidence that these two numbers are the same number? And then you read the question again. The question says, gaseous hydrogen iodide is placed in a closed container at 425 degrees Celsius, where it partially decomposes to hydrogen and iodine, following this equation. So all of the hydrogen and all of the iodine that are in the container all came from here. This molecule is HI. It's going to split apart to make H and I. Oops. If this splits apart and that splits apart, so now I have this, maybe they can get together and these can get together. So can you imagine a scenario under which the concentration of this in a one-to-one relationship is not the same as that? At equilibrium, these should be the same number. Okay? There's no excuse for them not to be the same number. So it's not just a coincidence. It's not the question writer being lazy. It makes sense. Okay? So, Kc is products divided by reactants. Products is H2 over I2. Reactants is HI. You put all the numbers in and you should get the right answer. Maybe, no, yes, no. No, not yet. What have I done wrong?
C charge
There's
2
two.
power 2.
Two molecules of reactants. I need to raise its term to the power of 2. Put the numbers in the boxes. Are we in any particular order here? 4.79 times 10 to the negative 4 times 4.79 times 10 to the negative 4. If I was feeling nerdy, I might square that. Divided by 3.53 times 10 to the negative 3 squared gives me a value of Kc. Oh, I don't know what the answer is. You have to tell me. This was 1527. Do we have an answer? gonna need to know what the log, the natural log is, and the inverse, it's how to find the exponent. Okay.
I got 6.4, 6.49 times 10 to the negative fifth.
Okay, I don't know. I don't know what the answer is, but I believe you. Because if you've done this right, because that's all you have to do, that should be the right answer. And small number squared divided by not as small number squared should make the whole number here get a little bit smaller. So it's probably, it looks like it's in the right order of magnitude.
I didn't start at the bottom.
You didn't?
No, I just said it's not.
Oh, well, then.
I got .018.
Okay. Which is more like a question that would be in the textbook. Yeah, I don't know.
0.018, sorry.
Okay. Which is why we show our work. Because if you don't show your work, and you don't include the square term, then you go all the way from the top to the bottom of this calculation. You give me a number that is the wrong number, it has no units, so I can't partially credit you for the units. You get the entire question wrong. Versus, oh, you show me what you're thinking. You show me that it's the concentration of the products divided by the concentration of the reactants. You show me the coefficients. You put the numbers in the boxes, and then you get the answer wrong. And I give you credit for having all of this right. And they say, that's a calculator error. If you came back to fix it, you would fix it. You would know where to fix it. Show your work. Okay. All right, 1534 is a step towards what's coming next. What's coming next is you got to figure everything out for yourself. 1534 kind of is the halfway house to doing that. So let's do 1534. Says a flask is charged with 1.5 atmospheres of N2O4 dinitrogen tetroxide. The flask is charged with 1.5 atmospheres of N2O4 and 1 atmosphere of NO2 at 25 degrees Celsius. The following equilibrium is achieved. After equilibrium is reached, the partial pressure of NO2 is 0.512 atmospheres. What is the equilibrium partial pressure of N2O4? And calculate the value of AP. Okay. This one is kind of straightforward because there is one reactant and one product. Product appears twice, but there's only one of them. Okay? here's what we're going to set up. We're going to write underneath our balanced equation what the initial concentrations are. And I'm going to leave this one up because it's the same thing that I'm talking about. It is not coincidence that both of those numbers turned out to be the same number, because they have to be. They have to be equal to one another. So when I started the reaction, I had 1.500 atmospheres of nitrogen tetroxide and 1 atmosphere of NO2. Underneath my initial rows, I'm going to leave a row that says change. And then I'm going to have a row that says equilibrium. Okay, so the question continues to read, after equilibrium is reached, the partial pressure of NO2 is 0.512 atmospheres. What is the equilibrium pressure for N2O4? I don't know. I gotta find that out. What is the change in the middle? I don't know. I'm gonna figure it out. And here's how we figure it. Okay. I started. I'm gonna look at the part on my table where I have the most information. I started with an atmosphere of nitrogen dioxide, and I ended up with 0.512 atmospheres. So the change in that number is I have lost 0.488 atmospheres. I have one molecule of N2O4 being responsible for 2 molecules